Hello, ladies and gentlemen. This is a presentation for imagining Wurer as a water city, a task under circular urbanism in parametric and urban design course. We are a group of 3 students, namely Ahalya Gandikota, Biniyam Gitana, and Muhammad Amin. So let's start our presentation from a quote of World Business Council for Sustainable Development. Everyone understands that water is essential to life, but many are only just now beginning to grasp how essential it is to everything in life. Its importance begins with food, energy, social norms, transportation, nature, culture, leisure, identity, and most importantly, our daily needs, from drinking, cooking, cleaning, and etc. Our challenge for Wurer is to provide sufficient water of appropriate quality and quantity to the existing developments as well to the new developments to come. While considering a water balance in which the left side of the equation equals the right side, in other words, the balanced use of the inflow and outflow in accessible, affordable, and adaptable manner. We try to redefine the challenge as aims. First, to offer a resilient and sustainable rural transformation, and next, to approach rural challenge with water sensitivity and use it as one of the driving forces for the new development. So, what does it mean? When we say resilient, sustainable, and rural transformation, we meant to integrate existing rural fabric with the new development first, and to use new development as a catalyst for spatial and social cohesion among the communities, and to create an accessible, well-connected, pedestrian-oriented street network. And what we meant by water-sensitive development is to design a water supply system for providing a safe drinking water to the locals and distributing it by gravity without the use of mechanical means as far as possible, and to protect streets from runoff and to replenish the groundwater. The methodology we have tried to follow is back and forth method rather than the linear one. So, first we tried to see the background study of the site and analyze the existing sites and surroundings. And first we put the boundary conditions as the total number of inhabitants to be 10,000 and water per person per day to be 50 liters. Then we tried to put the potential city center and generated the ring roads. And we get the first result by interconnecting this ring road with the generation of internal streets. Then as a second result, we try to follow the water network and get street networks. The third result is by positioning of the water tank in different areas and get an option for a blend of communal taps and direct access to water and elevating the water tank to supply water by gravity to each household. Then we get the fourth result by checking the rainwater runoff on the streets. The final result is driven from the adjusting streets and water network to reduce the runoff and get the hydrology-driven street network. Wurer is located in southern nations and nationalities, Gurage Zone, Chaha Warada. When we see the existing conditions of Wurer, there are different neighborhoods located apart from each other. This will make the infrastructure provision more challenging and costly, and also have effect on the social connectivity. Inside every neighborhood, there are existing settlements and agricultural land. The main highway in the center dissects the village into two. There are different social and physical infrastructures like mosques, churches, telecom tower, and healthcare. The flower farm and the water bottling factory provide the inhabitants work opportunity. When we select a possible area for development, first we consider it to be on the boundary of the village, and it should be an open land which didn't disturb the existing development, private farmlands, or green covers. One of the end product is a city which can reside 10,000 households, besides creating a social cohesion among the disintegrated current neighborhoods. We use the existing main street and observe where there is a relatively more number of neighborhoods, quarters, and an open land available. Putting this in mind and using the ring road algorithm, we try to define the city boundary and at the same time redirect the current main highway to outskirts of the development. This in turn creates an opportunity to connect the agricultural production to market easily and creates a less traffic and more pedestrian-friendly environment in the city center. Considering all this, we have put our finalized location of the city center, taking into consideration of existing significant infrastructures and using the algorithm of ring roads and city boundary, and we get this final output.
After setting a potential location for the city center, we tried to generate internal street network using the urban water-based street growth algorithm. We tried to take account the existing settlement by making a rough estimation of the existing buildings and people who are already there. Later, we manipulated the algorithm in order to generate street patterns for a city of 10,000 inhabitants, including the existing population. As we mentioned earlier, we tried to specify the possible open areas for a new settlement without interrupting the existing ones. Later, we tried to integrate both the existing and newly generated settlement to provide a holistic development approach. Our newly generated street segments possibly covered an area of 6.22 square kilometer, providing 1,000 square meter space per household and 5 persons in each of them. After getting the street pattern, we concerned about positioning the water tank to generate an efficient water supply network for our new city. While analyzing the topography of this specific area, we discovered that the terrain differences are very mild and an elevated water tower might be needed to provide an uninterrupted water supply to the future settlement with the help of gravitational force. Moreover, an elevated water tank could have some advantages such as they just not only preserve water but also energy. It helps pressurizing the entire water system using its height, and as a result, the pressure within the pipe network keeps the water free of contaminants. It's important to have an overview of how an elevated water tank functions in order to realize its importance. During the daytime, electricity demand is high, so running a pump might come to very costly, but having an elevated water tower would going to provide an opportunity to the water system to be run by itself using the pressure without using pump during the daytime. During the midnight, the demand of both the electricity and water are low, so the pump could run in order to fill the water tank. As the day starts and progresses, the demand of water will start to increase and eventually be supported by the storage of the tank. The pump itself might not be able to fulfill the demand of the entire city during the peak hours, but it's the water tank who is making the difference in the game. As the day ends, the tank will again be filled with water and get ready for another cycle, which is an ongoing process altogether. It's also important to know how elevated a water tank should need to be. Pressure within a body of water is related to the depth. The deeper the water, the greater will be the pressure. It can be compared to a virtual ocean under which we all live. The water surface is elevated storage tank represents the surface of the virtual ocean. Thus, a tank elevated to 20 meters creates about 200 kilopascal and the tank elevated to 70 feet creates about 30 psi of discharge pressure, which is sufficient for most domestic and industrial requirements. Based on the generated street pattern, we tried to formulate a best possible water supply network to provide as much water as possible to the households. We are considering 2 water reservoirs at 2 different locations of the city to provide maximum water supply. Among them, one reservoir is elevated up to 3 meters, considering all the buildings are one-storied initially. The other reservoir is positioned down to earth. After having an efficient water supply network, we tried to merge nearby existing settlements within the supply chain and rerun the urban water generative hydrology network analysis, which worked fine even after the integration of the existing households. We observed an average pressure of 1.7 bar on each supply points, which is more than sufficient for an uninterrupted water supply.
After having worked on the street and the water network, we used the runoff analysis to determine the street segments which are most affected by the rainwater. We then adjusted the direction of these streets to come up with a final street and drainage network. Though it is ideal to design streets which are in line with the gravity of water flow, it was quite a challenge. With the use of runoff analysis, we chose 5 most critical points affected by rainwater. The percentage of runoff was between 15 to 52%. We then adjusted the angles of these street segments to best suit the direction of natural rainwater runoff. The percentage of runoff was reduced to around 8 to 16%. Based on the runoff, we finally froze our street and water network. The blow up here shows the rainwater runoff by gravity and a possible drainage flow. Based on the pipe diameters, drainage lines 1 and 2 can be the primary and secondary lines respectively, and 3 and 4 can be the tertiary lines connecting to the secondary line. The runoff water from all the streets is directed to the river, which is in turn connected to the pump and then the reservoir. Through this task, we were able to come up with an optimized street and water network catering to 10,000 inhabitants with the use of parametric tools. We are now looking forward to further including the aspects of mobility and food in the coming weeks to develop a holistic design which is sustainable and efficient for the local community of Wurer.